Hello, we are Team EXYTE. We are going to present Urban Vision, a wide lens on all urban challenges. Urban areas are always changing and growing, but they still have ongoing problems. The main issues we focus on include infrastructure problems like damaged roads or broken streetlights, public cleanliness challenges such as litter and waste, and safety threats that put people at risk. Right now, it's hard to solve this problem fast because people often report issues late. Sorting and classifying problems is done manually, which takes a lot of time. There are privacy concerns when using images or videos from public spaces. To fix these challenges, we developed a system that uses advanced computer vision techniques. First, face and license plate detection models anonymize the images by masking sensitive regions, ensuring privacy is maintained. Next, these anonymized images are processed by a fine tuned CNN that detects and classifies multiple urban issues simultaneously. Each detected issue is categorized into its main category and relevant subcategory. Here you can see the main categories and their corresponding subcategories that our model is trained to detect. Data quality and preparation are key to effective model training. Our pre-processing pipeline includes data cleaning, label encoding, dataset splitting, image resizing, and normalization.
In our anonymization module, we targeted two key privacy risks that are face and license plates. For face detection, we fine-tuned a YOLO level name model in two phases. First, freezing the backbone for faster convergence and then unfreezing it for high accuracy. For license plate detection, we take a pre-trained YOLO 8 module. Once detected, these sensitive areas are expanded slightly and anonymized using Gaussian blur and pixelation. This ensures critical PII is fully protected in all processed images. For our classification task, we used a convolution neural network to classify images into one of 6 subcategories. We trained the model with binary cross-entropy loss and the Adam optimizer for efficient convergence. Early stopping was applied to prevent overfitting, with a maximum of 30 epochs and a batch size of 32. Throughout training, we saved both the best performing model and the final model for evaluation. Our classification model is built using a sequential convolution neural network architecture. It starts with a conv2D layer with 32 filters and a 3x3 kernel, followed by max pooling and batch normalization to stabilize training. This pattern repeats with 64 filters and again with 1 to 8 filters, each time increasing feature complexity while reducing spatial dimensions. After feature extraction, the output is flattened and passed to a dense layer with 1 to 8 neurons and ReLU activation for learning higher level representations. To prevent overfitting, we apply a dropout of 50%. Finally, the output layer uses a sigmoid activation function to handle multi-label classification across all subcategories. Our model achieved an overall accuracy of 80.7% with both precision and recall at 0.85, meaning it can correctly identify issues while minimizing errors. The F1 score is 0.84, showing a strong balance between precision and recall for multi-label classification. We faced four main challenges. First, class imbalance, which we solved using balanced sampling. Second, difficulty generalizing to new images, addressed with diverse validation and test sets. Third, threshold tuning, where we adjusted thresholds to better balance precision and recall. Finally, data quality issues, which we solved by cleaning labels and using multi-hot encoding. This concludes our presentation and thank you for your attention.